This is one of the first tensegrities that Kenneth Snelson had built. By the way, Kenneth Snelson is not the first person to is building what we now call tensegrities, because there was an exhibit in Russia in the 1920s, and they apparently did a whole bunch of things. Oh, it's a little hard to tell because the records aren't so great. But in any case, this is one. And if you can see, well, I have some models that I'll show later that are sort of variations on this sort of thing. I proved tensegrities like this some years ago with a colleague of mine, Maria Terrell. And we showed that they have a particular kind of rigidity that I'm going to discuss. Okay. Here's another thing of Snelson's. This is this is a natural thing. What you can take this basic Snelson with 3 bars, and you hook them together one way or another. What he has done is he's used, if you look closely, if you can see my marker, he's used several cables along the way in order to stiffen the structure. And even though it gets smaller as it gets larger, if he hadn't done that, the thing tends to be very wobbly, or you have to put an enormous amount of tension into the structure. Okay, so this is the kind of thing we mean by a tensegrity. So let's be a little careful about what we mean by a tensegrity. What I mean is a bunch of points. Yes, yes, please interrupt. Yes.
There's a question in the chat, so I'll alert you when such things happen. So it says, how is it affected by wind at that height?
If I get the chats, I don't know if I can see the chats here.
I'll read out the questions if they're in the chat. So okay, this one says, how is it affected by wind at that height?
This you'll have to ask Snelson. Because has anybody been there? I've been there to the exhibit at Washington, DC, but I would imagine that it sort of wobbles around a little bit. He tried to make it, it looks like he tried to make it as stiff as possible. But I don't have statistics on the displacement under wind pressure. That's a more engineering thing. I'm interested mostly in the geometry of the structure. In fact, so much so that some of these are really impractical. But we'll see. I had an argument with an engineer friend of mine, and I think he may have been right. Okay. Well, anyway, so this is the precise definition. I'm interested in the geometry of these things. And so I have a bunch of points sitting around in space, in the plane or in 3 space, or for that matter, even in higher dimensions. And between each pair of points, there is a bar. And the bar says that distance between those 2 points has to be fixed. A strut says, well, that distance can get larger, but not smaller. It can stay the same. The cable can get smaller, but not larger. And when you decide, or it could be no condition, and when you decide for each pair of points what that condition is, that you've got a tensegrity. In a way, a bar is like a combination of a strut and a cable, if you like. So these are some examples. The truss looks like a bridge, part of a bridge. I like this one in the middle. It's a spider web. It's effectively pinning the outside triangle and then suspending things on the inside with cables. Another one is this thing on the right, the Cauchy's arm. When you look at this thing, the 2 lower points, if you put cables in there, the 2 lower points can only move apart. They can't move together. So if you leave it unbucked, the thing has to increase. I'll mention that a little bit later, maybe on the next, maybe on Friday. Anyway, so is everybody okay with this? This is the background of what I mean by a tensegrity. Some of the students here, or maybe all the students here, have been discussing bar frameworks. And the question is, when are they rigid and what rigidity properties do they have? And I'll do some of that here, but with respect to struts and cables. Okay, yes. Is there a question? Actually, it's easiest for me if you just speak up. Yes. Okay, so the way I think it's commonly done is you designate the whole set of points. You label the points, and you want something to, a way of describing what the points are and calculating with them. So each of the points I can think of as a vector in some Euclidean space. And the bunch of all those vectors put together is the configuration. It's the bunch of points in their place in Euclidean space. Now, there's also the underlying graph, where the edges of the graph tell you, the edges tell you who's connected. And if they are connected, they have to decide to be a bar, a cable, or a strut. Or they could be nothing, but then you don't include it in the graph. So the whole thing is the graph together with the configuration. That's the notation. Just try to make things simple. Okay. Now, what I want to concentrate on are three basic types of rigidity. Now, the first is, just to emphasize, would be local rigidity. It means that with those constraints, the only thing you can do to the graph is move it around rigidly. So continuously. What it means that there's no other configuration nearby the original configuration that has the same, that satisfies those constraints, except when it's a rigid motion of the original graph. So I call that local rigidity. If you say something is rigid, that's generally what you mean. If it isn't rigid, it turns out there's a continuous motion of the configuration that satisfies the constraints all the time. Cables can get shorter. I'll show lots of examples of this. Global rigidity is when you can say, well, I have this one configuration in space, and the only other configuration in space that satisfies the cable strut bar constraints is rigid congruent copies. It could be reflections or rotations, or reflections and rotations of the original one. The sort of obvious other configurations that you could make. Nothing is pinned down. You can pin too, but that's another thing. So global is in your Euclidean space. It could be in the plane, it could be in 3 space, could be in 4 space, and so on. Universal rigidity is the same as global rigidity, but for all higher dimensions. In other words, you have something, let's say in the plane, and it's rigid in 3 space in all higher dimensions as well. So local means local, nearby. Global means in the same Euclidean space, and universal means on all higher dimensions. Everybody okay with that?
Was universal rigidity global rigidity in all higher dimensions?
Yes, exactly.
Okay.
Exactly. But it may live in a lower dimension. It has to decide in some lower dimension where it sits. Right. I'll show some examples. I think maybe that's the way to understand it. There's another type of rigidity that some of the students here, I'm sure, know all about. And this is what an engineer would want when they build a building. It's called infinitesimal rigidity. There's a synonym, static rigidity. And what it means is that there's no way of starting the motion except trivial ways. The p primes are sort of, if you know about calculus, it's the derivative of the start of the motion. And there can be trivial ways of doing it by rotations or translations or some nonsense like that. But except for that, if there's only those trivial starting infinitesimal flexes, then you say it's infinitesimally rigid. And the theorem is that if it's infinitesimally rigid, then it's locally rigid. But that's all. It doesn't say that it's globally rigid or universally rigid. But this is a standard engineering way of determining whether something is locally rigid. Okay? Okay, so let me show some more pictures. Here's an example. This is the main theorem I was mentioning. If it's infinitesimally rigid, then it's locally rigid. And these are some examples. The first two are easy ones. So if you have this guy is infinitesimally rigid, we'll say a few words about that. And what you can see, it's like a harp string. You can twang this thing and it vibrates back and vibrates back and forth here. This one, it's sort of the same thing. You can subdivide this cable by moving a point outside and then putting a strut and a cable in. The strut, I bend it a little bit so you can see when things are in the same line as the strut. The one on the right is a little tricky because what happens is that the three red vertices, the green thing is just there to show you that the three lines meet at a point. But these three vertices rotate about the green point. And infinitesimally, they don't actually rotate, but they rotate about the green point, keeping the outside three vertices fixed. And this cable, this, you don't have to move this, the right vertex, but this cable increases to the first order. It really collapses, but it's still rigid. All three of those things are rigid, but they're not infinitesimally rigid. So I find it's most interesting to understand infinitesimal rigidity if it isn't. So, this, I can't help but put in this picture of a whole bunch of us back in 1978. Is that right? Yes, 1978 in Syracuse University. Walter Whiteley and Ivo Rosenberg and Branko Grunbaum, Ethan Bolker, Ben Roth, Henry Crépeau, and me. And I think everybody's alive except Branko and Henry, as far as I know. Do you know, Tony?
I agree with you. I don't know any more than you do.
I see. Okay, so I couldn't resist putting this in. This old friend. Now, so some of these, there's easy ways of creating examples that are infinitesimally rigid or locally rigid, but sometimes they're not globally rigid. This thing on the upper left is a very simple example of a way of creating things that are locally rigid or infinitesimally. You start off with a triangle. It's infinitesimally rigid. Then you attach in the plane, you attach a bar to two of those edges of the previous thing, and you inductively build up this whole thing. And that's a very natural way. Not all infinitesimally rigid or locally rigid things are built up so easily. The really nice example is a convex triangulated polytope. And the idea for its rigidity goes all the way back to Cauchy in 1813. And the simplest non-trivial example is a octahedron, like a regular octahedron like you see in the picture. It's rigid. It's, when you build it, it's sort of obvious that it's rigid, but then why? And Cauchy gave a very nice proof, except he made a little mistake. But the idea is that it's the only way, it's not quite globally rigid in the general sense, but there's no other way of assembling that polyhedron, making it convex. A very nice result of Cauchy. The mistake wasn't caught until later. The mistake is actually in a tensegrity result. The one on the lower left here is a triangle with these tabs that are put in, and the tabs flop in and flop out. And so that's one way of have something that's not globally rigid in the plane. There are other realizations of this thing in the plane. And this thing on the right is a ring of 6 tetrahedra, and it has some very nice properties, but I just threw that in because it's related to another problem. But anyway, so any questions or comments? No? I can't see a lot of people here.
Is that tetrahedra one in 3 space or in the plane?
Pardon me?
Is the tetrahedra in 3 space or is it just the?
Oh no, it is in
of the
3.
plane?
It's in 3 space. That's right. It's 3 space. But apparently, it's not globally rigid in 3 space. Right. Yeah. The octahedron is not globally rigid either, but in order to find the other configuration, you have to move the vertices down. By the way, struts can go through each other, cables can go through struts. That in this setup, you don't worry about. When you build it, if you have struts or even cables that cross, you can't just let them go through. You have to pay attention to that in a practical situation. But as far as this theory, you don't pay attention to that right now. If things are prevented from crossing each other, that can restrict the motion. It could make something rigid. That's usually not done. Okay. Oh no. Yeah. Okay. Now here's something that's a little bit more typical for not being universally rigid. In the plane, if you have the 4 triangles like this on the upper left, the question of whether there's another way of folding that object back into the plane again, it has to do with the 4 angles on those triangles around the central vertex. If those 4 angles add up to 360, it's in the plane. But if there's another way of folding it around again, you put a plus or minus on those angles, it could go back in the plane again. And generally, that won't happen. The sum of the angles, when you subtract any number of them, won't go to 0 or 180 or anything like that. So that thing is, you can't reassemble it in the plane, but it flexes right up into 3 space. The same thing is true if you take the cone over it in the upper right. That is globally rigid, but in 3 space, but not universally rigid. The thing has motions in 4 space. Hard to imagine, but it's there. This thing on the lower left is a paper that is a result from a paper that I wrote with Shlomo Gertler, that this is a bipartite graph. All the reds are connected to all the blues, and if the reds and the blues can be separated this way, it is not universally rigid. But this thing, if you're careful, is also globally rigid, certainly rigid too. So that's not at all obvious. And there's another one with another bipartite graph in 3 space, where I think they're all bars. So some of these questions are not trivial, but in fact, I think global rigidity is incredibly difficult. And I know Tony has been talking about global rigidity mostly in the plane. Is that right, Tony?
Yes.
Yeah. Yeah. And that makes it easy.
And all generic.
Easier. And okay. And this is another one, I think in the conference here, one of the people talked about this. This is a flexible octahedron. The graph is an octahedron. If you make this out of paper and leave some of the triangles open, you can flex it flat in the plane, so it's rigid in the plane, but it moves up in 3 space and back down again. It's not globally rigid in the plane. It's a little hard to believe, I think, but if you make it out of paper, you can do that. I don't have any right here right now, but I just thought I'd throw that in. Okay. The stuff I want to talk about, the thing I want to talk about is the stress. Now, a stress, as far as I'm concerned, as far as the geometry is concerned, is just a scalar. It doesn't have units. This is not engineering so much. It's just a scalar number. And what it is, it's a scaling times that you use against the vectors that represent the edges of the graph. And the important thing that scalars do, these stress scalars do for you, is that they, at each vertex, this is the summation here in the middle, at each vertex, let's say J is the vertex, and you look at the vertex pi minus pj, the difference of the 2 vectors, where you fix one and you look around that vector, and if you scale them so that the sum of those scaled vectors, when you add them, is 0, you say that it's in equilibrium. If that's true for each vertex, you say the whole thing is in equilibrium. Now, if you have a graph with cables and struts, I would say that the yes, I hope I read this right. So when you put a scalar on a member for a stress, it's proper if it's positive for a cable and negative for a strut. And I think this is important. I had an argument with Walter. Walter's not here, I assume, poor guy. Walter wanted to reverse the roles of cables and struts. Later, we're going to see that there's an energy function that's related to this scaling. And if you do it Walter's way, he'll want to maximize the inherent energy in this energy function. And that just rubs me the wrong way. It's important that you, at least for later discussions, that you pay attention to the signs. So if it's a proper stress, it's positive for a cable and negative for a strut. Okay, for a bar, you don't care. Okay, any argument? Okay. Okay. One of the nicest results, I think, is this result of Walter Whiteley and Ben Roth, 2 of the people in that picture. That is, there's a lot of discussion about bar frameworks and their rigidity and their infinitesimal rigidity. And for bar frameworks, it turns out the criterion, you can use the standard criterion by infinitesimal motions and that sort of thing, infinitesimal flexes. But what is what this theorem says is that it sort of breaks it down to 2 pieces. What it does is it says, well, if you have a tensegrity, then you first replace all the bars and cables, all the cables and struts with bars. Everything is a bar. And you ask, is that bar, is that bar framework infinitesimally rigid? It's like you play like you're an engineer. And if it is, then you ask the second question, is there a proper equilibrium stress? It has to be non-zero on all the cables and struts. That's important. If it isn't, it doesn't say anything. If that's true, then the thing is infinitesimally rigid as a tensegrity framework. I'm not going to give a proof here, but it's essentially linear algebra. All this is linear algebra. All right, now one of the things here you can see is that if as a tensegrity, it's infinitesimally rigid, if you reverse all the signs of bars and cables, the equilibrium condition will still be true. Because the first condition doesn't say anything about, the equilibrium condition doesn't say anything about the bars and cables and stuff. And so you could just change all the signs and it'll still be infinitesimally rigid. But later we'll see with global rigidity, or more properly universal rigidity, it does matter in many cases whether if you reverse the sign of cables and struts, it falls apart. Now, one of the things that started my interest in this was a bunch of lectures in Lost Mathematics by Branko Grunbaum, one of the people in that picture. And what he noticed was that there were some tensegrities in the plane such that when you put bars and cables and struts down in one way, it was rigid. You could just tell that it was rigid. But if you reversed it, it wasn't. So it wasn't infinitesimally rigid, because this theorem would say that would be if you could do that. Anyway, so that's one comment.
Can I ask a quick
Yes,
question?
yes, please.
So if I have this correct, infinitesimal rigidity and static rigidity are equivalent for bar joint frameworks.
Yes.
So then is, I guess my question is that not true for tensegrities? Because this is saying that if you consider the equivalent bar joint framework, it's infinitesimally rigid. So then there should be no proper equilibrium stress on the bar joint framework. But then you're looking for one on the tensegrity.
No. So to be statically rigid means that there's a load, an equilibrium load, what do you call it? Statically reasonable load on the thing, and it can be resolved by stresses in the framework, right?
Yeah.
So it's like a truck goes over the bridge, and then it doesn't move. The interesting thing is static rigidity is a little unreasonable in the sense that when it has an equilibrium load on it, it doesn't move at all, and it resolves the load. But that's okay. That's what it means to be infinitesimally rigid. Here, for a tensegrity, it's the same thing. If you have an equilibrium load on the thing, that has nothing to do with bars, cables, and struts, whether it's an equilibrium, but it has to resolve the load. Well, you think of it as a cable. The cable, the tension in the cable, the stress in the cable or strut that results, it has to be proper. So every equilibrium load can be resolved by a proper stress, not a proper equilibrium stress, of course, because at each point it has the external load. Okay, it's the same thing, except you just put in the word proper as far as what the equilibrium, what the stress that resolves the load is. Okay.
Okay. Thanks.
Yeah. So that's very reasonable. Some of those things, but it could be, and you think, well, I'm going to reverse it, but then you don't have to necessarily reverse the sign and things. That's the other thing. You can't reverse the sign, but if you reverse all the cables and struts, then that would be fine. All the cables are struts, and all the struts are turned to cables. Right. Okay. So now one of the, let's see. Yes, so the thing is, for this, what I originally did, I don't want to go into this with spider webs, but originally I thought, well, if you pin a bunch of vertices and then put any stress you want, the thing will come to equilibrium, and it's easy to show that there's a unique configuration that resolves where it comes down to a minimum energy. And then I realized that, well, it's sort of more convenient, but a little trickier, if you simply add up the squares of the distances of the lengths and weight it by a stress, an equilibrium stress. Okay, so it's a quadratic form. In other words, there's no linear term and there's no constant term. It's all a quadratic form on the space of configurations. Okay, that's it. It's a little dumb, but it works. Now, if you have an equilibrium stress on a given configuration, actually the equilibrium stress, in a sense, it doesn't have anything to do with the graph. The sign of the stress tells you whether it's a cable or a strut. But if you have this equilibrium stress, which is a number assigned between every pair of the numbers, if there's nothing there, that number is 0. If it's at an equilibrium stress, then this energy function is 0 if it's at an equilibrium. So that's just basic linear algebra. I hope that you can accept it, and I think it's you'll see more about it this later. I'm trying to get the jargon, the technology out. So here's a picture.
Bob,
Yeah.
could I ask a question about this? So how am I supposed to think of the squaring operation here?
It's the length.
These are
squared.
vectors.
It's the length of the member squared. But you
so
take it in
we're
any
just
configuration you want, right? Pardon me?
Okay, so is there a length missing in this displayed equation?
Qi minus Qj is the difference between the vectors, and that vector squared times itself, that's like the inner product. Oh, I should have put straight lines. I think of them as vectors multiplied by each other.
Okay.
So that's why I write squared.
I see.
Sorry.
The vector transpose times itself. Okay, that's fine.
Yeah, so I mean this Qi minus Qj dot Qi minus Qj.
Cool.
Right. Or if you like, it's the length of the vector of the difference between them squared. So it's very simple. You just take the squared length of the distance. Okay. So here are some examples of stresses. I like this one on the left. It's very simple. It's the first thing. It's a complete, everybody's connected to everybody. It's a complete graph, but okay. This is what I was saying a little bit before. This stress is just a scalar assigned to each cable or strut, but it's not a force per, it's a force per length more than anything, rather than a force per cross-sectional area. So it's a little funny from the engineering point of view, or from the physics point of view. But this is precisely it's just a number associated to each cable or strut. And this is in equilibrium. Now, the first thing is you have to look at this thing on the left and convince yourself it's in equilibrium. But if you take P3 minus P4 and P1 minus P4 and subtract P2 minus P4, you don't add P2 minus P4, you subtract P2 minus P4, all those three vectors add up to 0. It's a -1, and people want to put a square root of 2 in there. Don't do that. It's you want to add it as it says. You just reverse the sign. And they're all the same. So it has to be the same way. The one on the right is very similar, but it is, how to put this? This is, the scaling is different. And when you draw a few pictures, you can see that this is right. So this is the typical kind of stress that you get. I don't want to go over here too much. So, all right, so now it turns out that that energy function, it operates, it's so simple. What it is, if you look at this energy, let's go back and look at it a bit. This energy function is the sum of the squares of that. If you take this vector, you take the difference in the x coordinates, the difference in the y coordinates, and if there are z coordinates, you take the difference in the z coordinates. You square them and add them up. Each coordinate is absolutely oblivious to the other coordinates. So the energy function, it looks like, what's this higher dimensional stuff? It's really just the difference in the x's. The difference in the y's, there are different values for the y, but it's different. So I'm claiming that when you look at this thing, you can just look at the way the energy function acts on each coordinate. But the energy function officially is, the quadratic form is given by a symmetric ND by ND matrix. So if it's two-dimensional, it would be 2D, 2n by 2n. But all of the things that operates the same way on each coordinate. So just look at it one coordinate at a time. Just look at it for one coordinate. Now, here I did an example. If you look at this guy, the stresses are all plus or minus 1. Now that may be confusing who's who, but it doesn't really matter too much. You just look at the, so when you look at this as the quadratic form as a symmetric matrix, which you can always do, then it turns out that the matrix of the quadratic form is this, as I've said it. Now I have to tell you what the numbers are. This is 1, 2, 3, 4. This is P1. The 1, 1 is this. Now, one of the things about this matrix, so this matrix is given to you. I like to say I didn't make it up, but I did. But it's what it tells you this quadratic form is. And what it is that the off-diagonal entries here, like 1, 2 here, is minus 1. But in the matrix form, it's minus the stress. I have to do it that way in order to get things to be what I said, what I said this thing was. I've said this is the quadratic form, the energy function. Once I've done that, I'm just rewriting it in terms of a symmetric matrix. So that's the important thing. The off-diagonal entries are minus the stresses between I and j. Like the stress between 1 and 2 is plus 1, but in the matrix, I have to put in a minus 1. And then just to make things sort of fancier, the diagonal entries are such that the sum of the whole thing is the sum of each row or column, the same thing, is equal to 0. Now, this is the quadratic form that energy function gives you. I have to follow those rules. Now, I realized last night it would make it a lot easier to see how this works, to see what the equilibrium equation is. And now I think this helps. So for this matrix and this object on the left, the triangle on the left, the equilibrium equation turns out to be this. The top row of this, let's say, I'll call it a configuration matrix, if you like. is all ones. That means when you multiply the top row times the top row on the left times the first column, the sum has to be 0. Oh, whew, it works. And then the second row, which corresponds to the x coordinates, and the third row, which corresponds to the y coordinates, each of those times each of the columns equals 0. So the whole matrix product is 0. What's going on is that this represents vectors in the, well, in this case, the co-kernel, the kernel on the left of this stress matrix. Ones have to be in there, that's just the way it is. And the x and y coordinates each define this. So the rows are the vectors in the kernel of the stress matrix, and the columns represent the configuration given by those rows. So columns give you the configuration with an extra 1, I'm thinking of it in the z-plane, and then you give all of the things in there. And looking at it this way really makes a lot of the things that are coming up later much simpler, I think. So it always looks like this. You have a 1, P1, 1, P2, 1, P3, and so on. And you multiply that vector on the left times the stress matrix, it's equal to 0. So the stress matrix does that. That sort of gives you the setup for the stress energy setup.
Can I ask a question about this matrix here on the right? It's got a very odd property that the dot product of any two rows is either 4 or -4.
Oh, you mean on the stress matrix?
Sorry, not of any two rows. Maybe that's true as well, but any two columns in the stress matrix.
Yeah.
Is that explainable using things, or is it just a random fact for this matrix, for this particular one?
Well, I'm not sure what the dot product of those two rows means. It might very well mean something. I don't know. This example is a little unrealistic in the sense that for most examples, you don't have everybody connected to everybody. It's not a complete graph. So in general, there'll be tons of zeros in there. And each row in the stress matrix or each column in the stress matrix, that corresponds to something like the stresses at every vertex, the sum of the stress vector at every vertex.
Mm-hmm.
Yes. Also, it's possible to, well, there's a question of whether this matrix is positive definite or not. That's the thing that comes up later. And maybe we'll get to that. I don't know. I'm going to just stop this when the time is out. The time is done. So we'll be done in a little bit. And I'm going to continue this on Friday. But I have a lot of examples to look at too. So as offhand, I don't see anything like that, but the matrix itself, the stress matrix itself, if it's positive semi-definite, can be written as a product of other matrices. And if you know about Lovaas's work, he thought of things that way. So the definiteness of things is very useful. And the kernel of this thing is very useful. That's true. So offhand, I don't know offhand what the inner product of the two rows or columns of this thing means, to tell you the truth. No, it's either 0 or 1. Yeah. I don't see anything offhand, but that's an interesting thing. Okay. Okay, so the thing about this is that you get information about the stress matrix, and so a basis of, if you look at the stress matrix, a basis for the kernel or co-kernel, however you want to think of it, that looks like this stuff over here. So the rows over here form a basis for the co-kernel of this matrix. And that gives you a lot of information about other things, other configurations that have that configuration such that it's in equilibrium. It's important where you have the stresses to find those configurations that have that stress. Okay, that comes up in at least 2 points. Another point is that if the matrix itself is positive semi-definite. Now, this statement is if you have a symmetric matrix and it's positive semi-definite, if you think of it as a quadratic form, the only thing that's zero is the kernel. If you have something, it's always non-negative, and you have a linear function like that, the only way the thing can be zero is if it's in the kernel, right? Right? This is sort of basic linear algebra about symmetric matrices. That's important because it's easy to tell when things, or it's natural to tell when things are in the kernel. The important thing is that the kernel of the stress matrix, everything in the kernel, if you have a basis for the kernel and you have anything else that's in the kernel, it's an image of this. There's a linear combination of the basis vectors that's the other one. That's this other bunch of zeros or other bunch of things that are in the kernel. Then that corresponds to an affine image. Affine image is a linear plus a constant. And that's a very, very useful kind of information. Now, maybe after this is related to generic global rigidity. So maybe I'll go through this. You've heard about this already, but this is a numerical condition for generic global rigidity that started basically with my student, former student, Bruce Hendrickson. So if the configuration is generic and you have a bar framework that's locally rigid with an equilibrium stress, and the matrix, now you realize that the matrix has the ones in the kernel. So that's the rank has to be down by that. And each x coordinate, y coordinate, z coordinate in the affine, in the span of this thing contributes to the kernel and subtracts from the rank. So the max rank is n minus d minus 1. If the max rank is n minus d minus 1, then the graph is, as the bar graph, is globally rigid in the generic case. Now, you've heard about this from Tony about generic global rigidity. This is sort of like, this plays the role like the rigidity matrix for ordinary rigidity, local rigidity. Okay, I don't want to go into this too much, but this is a sort of basic observation. It's a criterion for generic rigidity. It's sort of not obvious why, but that's another discussion. And then Gertler, Shlomo, and Dylan showed the converse, that in fact, if it's a generic configuration, the rank of this stress matrix is the critical determinant. If the rank is maximal at a generic configuration, then you know the thing is globally rigid. And it turns out, I think you've been hearing about the generic global rigidity in the plane. And Bruce realized that if it's generically globally rigid, then it has to be three connected. If it's not, if there are 2 points that separate it, it flops from one to the other. That's pretty clear. And then it has to be redundantly rigid. And this was a very nice idea, but that's necessary and sufficient. It was his conjecture and approved by Jordan Jackson, and it's been proved and reproved and done in different ways in the plane ever since. So you don't need stress matrices anymore, I guess. Too bad. But that's part of the situation. Okay, now the next thing is affine motions. And let me stop here. I'll maybe take this a little bit later. I want to do some pictures to show things that are rigid in the plane. This is largely what Branko Grunbaum asked. And I don't have an example here. Well, for instance, this K33 on a conic, this thing. This is a hexagon with opposite vertices connected. That thing is, if you reverse the role of cables and struts, it's not rigid. But it is rigid when you put cables on the outside. So these are some examples, and I'll talk about that next time. So I think we're running out of time. Are there any quick questions or not so quick questions?
I had a quick question. There was the Gortler-Thurston result you had on the previous slide. Is that separate?
Wait, where did that go? Yeah, there it is, yes.
Is that different than the Gortler-Healy-Thurston result that seems similar? Yeah, about the existence of a global stress being necessary for global rigidity.
Yeah, that's sort of what this is. Did I forget Healy?
This is the Gortler-Healy-Thurston result.
Okay. I just want to make sure it was separate.
Yeah, did I forget to put Healy in there? I'm sorry, that's my bad thing.
Okay.
Yeah,
Thanks.
yeah, right. So this is more heavy-duty algebraic geometry. Even I would say maybe it's simpler. I'm not sure. It's not that trivial. The result that if the stress matrix is a maximal rank, then it's universally, it's globally rigid. However, it's a little tricky because you can have a infinitesimally rigid, generically infinitesimally rigid, infinitesimally rigid, and with a stress matrix that has maximal rank, you can have it sitting there in front of you, and it won't be globally rigid. Frustrating, isn't it? But you have to say generic, and then it forgives all else. That's why I don't like generic. So you never know what generic is. So for instance, this thing that comes back here, where'd it go? Here, this one. Even as a bar framework in the plane, this little thing in the plane there is, well, maybe not that. Let's see. Where did it go? Oh, here it is. This one in the plane. This is a bar framework in the plane. It's certainly infinitesimally rigid as a bar framework. It's also, the stress matrix has maximal rank, whatever it is, 4 minus 2 minus 1 or whatever. But if I play with the angles here, if I make the angles so that plus minus those internal angles adds up to 0, whoops, the thing is not globally rigid. It folds over on itself. It committed the sin of not being generic. It's too bad. So you never know what generic is. That's the problem. However, for universal rigidity, we'll see later that it is different. That, or at least I think it's different, because if you're given a particular one, you do a calculation or you combine things and you can actually say that baby is universally rigid. If it's universally rigid, it's certainly globally rigid. That's often the case for a particular framework, that it's universally rigid. That's how you know it's globally rigid. And we have a theorem, Shlomo and and I don't know, maybe Lewis gets in on this, but that if you have something that's generically globally rigid, there is a configuration. It may not be close, but there is some configuration that is universally rigid at a generic point also.
So Lewis will give talks about this next week.
Yeah, universally globally, universally globally rigid. Yeah, universally generically rigid. Sorry. Yes, that's right.
So I have a question.
Yes.
Your result that says generically, if you have a maximum rank stress, then that implies global rigidity. Do you think it's possible to weaken the generic hypothesis substantially?
Oh, that would be wonderful, actually. But you need something. The question is, nobody knows what the generic condition is. That's the strange part. For this thing on the left, this guy on the left, I know what it means. I can tell when that thing is globally rigid. That's an easy case. But to weaken it, that actually I think would be good news. But to weaken it, what you could do instead, I would say you want to strengthen it. You want to make it universally rigid. Except universally rigid things aren't typical. They're not generic, usually, or the regions that are universally rigid can be open, but the regions where it's not universally rigid, but it's still globally rigid, is also open. So how do you tell the difference between those two? So you have an idea? You have an idea to show it? There's something that shows you something is globally rigid?
No, sorry, no idea.
Without showing it, it's universally rigid. Yeah. There's one result, I have one result I'll mention next time, the only proof I'm going to give, where you can show something is globally rigid if you show something else is globally rigid. And it's just global. It's not universal necessarily, as far as I know. But it's a weaker statement to see the second one. But that's another story. So I apologize to some of the tensegrity people. We'll see some more examples that are universally are rigid. So we have some of these. Let's see. Oh, I'm going the wrong way. It's some of these. I'll talk about some of these, which I particularly like. Some of these kinds of subjects, and they're the way of combining tensegrities to get other tensegrities that are especially universally rigid. And I'll talk more about universally rigid next time, especially. It's a very nice idea. We're universal, it seems like it's God-given. Global, I don't know. The devil's in there. Okay?
Okay, great. Thank you, Bob. Yeah, and thanks everyone. We're a bit over time, otherwise I would have asked to see some of Bob's nice models that you can see in the background, but maybe that can be on Friday.
Yeah, I'll talk more about those models later. Yeah, on Friday. I knew this, I have too much for today, but I hope I have less for tomorrow. I'll skip some subject next time if I need to. I want to get to the good ones.